In many different places in computer science, there is a need to define sets in an inductive way, and that's going to be the case in this course when we will discuss about patterns, when we will discuss about, for example, languages that are being accepted by different types of automata, but this is going to be the case in many other types of discussions in different places in computer science. So I would like in this lecture to discuss about how sets can be defined recursively or inductively. And the typical structure you will see in such definitions is very much resembling the structures we have seen when we discussed the induction principle. So a set can be defined inductively, or you can say also recursively, starting from a smaller set A0 of so-called initial elements. So you will see a definition consisting of, first of all, this sort of condition that says A0 is part of the set that you want to define, and this is the induction basis. It's resembling quite a lot the induction basis we have seen from the induction principle. Then in such recursive definitions, you will see a second condition, and this is resembling the induction step from the induction principle. And that's going to be something like this. It's going to say if an element A can be defined in some way in terms of some elements A1, AK that already have been established to be from set A, then also the element that you are looking at is from set A. And this again looks pretty much like the induction principle, where we were establishing a property for a natural number in terms of the property having been established for some smaller values of that number. And finally, in such recursive definitions, there will be this third condition that will say something like A is the smallest set satisfying properties 1 and 2. This can also be formulated in a different way. You can also see a definition saying the only way to get elements in A is through repeated applications of these conditions 1 and 2. There is no other way to have elements, and that's equivalent with this condition 3 formulated as A being the smallest set satisfying properties 1 and 2. So this is the general template for how to give recursive definitions. The exact details of what the induction basis is and what the induction step is going to differ from case to case. And I want to show you in the remaining of this lecture, I want to show you just 4 different examples on how sets can be defined following this pattern. So here is the first example I want to show you. I want to define the set. I'm going to denote this by 3n. So I'm going to define this set as a set of natural numbers divisible by 3. And obviously this can be defined in several different ways, but I want to follow this particular pattern I gave for a recursive definition. So I'm going to, just following this, I'm going to say, this 3n is going to be satisfying the condition that 0 is an element of this set. And then I'm also going to say if n is an element from my set, and so is n plus 3. And obviously I'm going to say, just like we will always say for recursive definitions, is going to be that 3n is the smallest subset of n satisfying 1 and 2. And so when you're looking at this, you will realize obviously that our definition is going to be 0 is included in there, and because 0 is there, by applying condition 2 you realize that 3 is in there, and then 6 is in there, and 9 is in there, and 12, and so on. So this seems to be, and obviously it's an infinite set, so this seems to be exactly what we wanted to define. One observation I want to make is that, as a matter of fact, if you take the full set of natural numbers, and in fact, even if you are excluding from this set numbers 1 and 2, for example, so these also satisfy conditions 1 and 2. This is easy to see. If I take the full set of natural numbers, obviously 0 is an element in there, and for any natural number, obviously also n plus 3 is a natural number. But still, this is not what we wanted to define. So what I'm saying is that this third condition, saying that, you know, we are focusing on the smallest set satisfying properties 1 and 2, this is really crucial. If you don't take that into account, you might define larger sets that in fact are not really in the focus of you know, what you really want to define. Here is another example that is going to be really important in everything that we discuss in the second part of the course. We are going to discuss about languages and about words and about letters, and that's going to be related to the input of our various automata. So I'm going to introduce here a number of terms, and that's going to be, I'm going to define what an alphabet is, and I'm going to define what a word and what a language is. And some of these are I'm going to give an inductive definition, but just to make sure, I'm going to introduce first the basic terminology, and then I will show you the inductive definition of the set of all words over a given alphabet. But I'm starting with, in this example, what an alphabet is. So for us, an alphabet is always going to be a finite set. Very often we are going to use for an alphabet, we are going to use letter sigma. An element of an alphabet is going to be a letter, so this is simply going to be just an element of the alphabet. And then we are going to have the notion of words. So a word over alphabet sigma is going to be simply a sequence of letters. So it's going to be something like A1, A2, AN. So simply letters, if you like, listed one after the other ones. All of these A's are from sigma. And this includes even the option of having the empty word. So empty word being, a sequence of letters of length 0. So you essentially have no letter. And I'm going to use for the empty word symbol epsilon. If you look over the internet or you check other textbooks, just be mindful that the empty word can be denoted in other sources with lambda or sometimes with 1, but throughout this course I'm going to use epsilon for the empty word. I'm going to denote by sigma star. This is going to be the set of all words over sigma. So if you think about what sigma star contains, so this is going to be obviously the empty word is in there. Then you have all the letters from your alphabet. Those are going to be words of length 1. So in terms of the sequence of letters being just 1, so you have all these letters that sigma consists of. Maybe I'm writing it here. Sigma is A1. Let's say a P. So I'm going to have all these letters. Then you will have all the words of length 2. So A1, A1, and A1, A2, and so on. Maybe A1, AP, and so on. So then you will have the words of length 3 and of length 4 and so on. So this is obviously an infinite set. I also want to define the operation on words, concatenation. So the concatenation is going to be denoted by a dot, and this is a binary function that takes as an input two words and gives in the output a word. And this is going to be defined like this: if u is say a1, a2, am, and v is another word, let's say b1, b2, bn, and ai's are letters, and bj's are also letters, then the concatenation u dot v, and very often we are even going to skip this this dot when it's clear that you have a sequence of letters. We are not going to indicate specifically that there is a dot between every pair of letters. So the concatenation of u and v, it's exactly what intuitively you would expect from concatenation. You would first write all the letters of u, and then we are going to write all the letters of v. So that's another word over sigma star. So, as a matter of fact, we can also define inductively. So here is where my example of an inductive definition of sigma star. So rather than just saying, just enumerating these words, which is obviously a very incomplete way of giving this set and maybe slightly confusing, I can have this very precise inductive definition, and this is going to go like this. First of all, I'm going to say that the empty word is always part of sigma star, and the second condition is going to be if a is a letter and u is a word, then a u, or a concatenated with u if you like, is also in sigma star. And finally, the third condition, as usual, is that sigma star is the smallest such set that can be defined, that satisfies conditions 1 and 2. Here is another example that's going to be useful for us in this course, and you will certainly see it also in some other courses throughout your studies. This is the example defining the set of arithmetic expressions. So what this means is that you have a number of variables and you are building all the correct arithmetic expressions over those variables, meaning that you can add them, you can multiply them, and you can put parentheses between them. If you want to consider minus also over these variables, that's also fine. So I want to define this in an inductive way, and it's going to be like this. First of all, I define the set of variables. So these are going to be, I will have a finite set of variables, x1, xn. And I'm also going to have, these two operations, addition and multiplications, and these are going to be binary operations. So they will need two inputs, and the inputs are going to be arithmetic expressions, and the output is going to be also an arithmetic expression. And also I will take minus as a unary operation. So this can be applied to a variable or to an arithmetic expression, and the result is going to be an arithmetic expression. And moreover, I will also consider the parentheses, the left parentheses and the right parentheses. And when we define this set of arithmetic expression, the primary focus is going to be on these parentheses being correctly closed. If you open a left parenthesis, the right one should close in a correct way, in such a way that inside you have a valid arithmetic expression. So that's going to be the focus of how we are going to formulate our definition of what arithmetic expressions are. So our definition is going to be the set of, so I'm going to define it by E, the set E of arithmetic expressions over X is the smallest, and remember our condition 3 that could also be formulated as the smallest set. So this is the smallest set of words over alphabet. And here is, I mean, in an arithmetic expression, obviously you can have plus, you can have multiplication, you have minus, you can have parentheses, and you can have variables as well, such that these two conditions are satisfied. So first of all, we will say that any variable in itself is an arithmetic expression. You can say, you know, x1, and just in itself that's going to be an arithmetic expression. And the other condition is going to be if you already have two arithmetic expressions, then you will also have that parenthesis E plus F close parenthesis. You will also have that E times F left parenthesis in the beginning, right parenthesis in the end, and parenthesis minus E and right parenthesis. All of these are also arithmetic expressions. So that's it. This is the definition, the inductive definition, and it's maybe surprisingly compact, thinking about what we really want to define, but it works fine because, as I said, the focus is really on these parentheses. The parentheses should be placed in such a way that inside you have a valid arithmetic expression, and the whole point of this definition is to observe that you can build larger arithmetic expressions by combining two existing ones with plus or with multiplication, and you put parentheses between, around them, to protect them with respect to further operations you might want to do with them. And the same applies also to this unary operation minus. And obviously you could have more operators depending on how rich you want your expressions to be. Maybe you want sometimes also to have fractions and other things. So for example, you could have, you would obtain, like I said, a single variable. That's an arithmetic expression. But you could also have, for example, things such as x2 plus x1 times x3 times maybe x2 plus x4. And because of the way that we define this, you will have to have these right parentheses to match this left parentheses in here. So all of these kind of things are going to be inside our set of arithmetic expressions defined through this inductive definition. Finally, this is yet another example I want to introduce, and also this is going to be very useful in a number of places in this course and in other courses. I want to define the set of binary trees. And they are very useful. For example, if you think in terms of decision trees, if you go towards artificial intelligence or machine learning, but they are also useful in terms of thinking about compilers and about the computation tree of a certain device. So they have applicability in a number of different fields. And we can define these binary trees over a set of variables. In my case, just to keep it simple, I'm going to have just two variables. So maybe I'm writing over variables x and y. And this is not a restriction. You can have more variables, but just to keep it simple in this example, I'm going to take just these two variables. And also binary trees are about operations you are doing on these variables, and more generally operations between binary trees being combined to give you larger binary trees. And I'm going to just take two different just two different operations, if you like, or two different labels. If you want operations here, I put in the parentheses f and g. And again, this is not a restriction. You could have more labels, more operations to have a wider expressive power over these binary trees. But the set of binary trees denoted, let's say 3, over the set of variables x, y, and labels or operations f and g is going to be the smallest set such that, and condition number 1 is going to be obviously that the variables in themselves are going to be trees for us. And the second one, this is going to be if you already have defined two trees. So if you have already T1 and T2 trees, then you also have that f applied to T1, T2, and g applied to T1, T2. These are also trees. And so I also showed something, with an illustration, but I just want to comment here. We wanted to define a set of binary trees, and I want to trace the, the significance of this word binary. So what this binary means is that the operations that you are working with, this f and g, they are binary operations. So both f and g, they take two inputs and give you one output. So that makes these trees being binary. The effect of all of these operations can be traced to their two inputs, and you can go from level to level throughout your tree. The other comment I want to make is that very often trees are shown in a graphical way, and I want to show you how this is done. So if I will take here just a few examples, if I take this simple tree y, y is a variable, obviously is a tree. Maybe I take also this tree f of say y and x, and if I take also this tree f applied to g of x, y, and then applied to x. So if you want to show this in a visual way, like usually trees are being shown, for a tree consisting of just a single variable, you simply write this variable, and there is nothing else you need to do about it. This is a tree consisting of a single node, and that node is represented by this letter y. Sometimes you have a circle around y, sometimes you have a dot and y written as a label next to y, but in this example I'm just going to write simply y here. And in the case of this tree, what I'm going to show is, first of all, this tree is obtained by applying f. So I'm writing f, and I'm showing with two lines the inputs that this operator f is applied to. And here I'm going to write y, standing for the first input of f, and here I'm going to write x, standing for the other input of f. And what this is supposed to show you is that you have a tree that's that has kind of two layers. One layer is the layer of this operator f, and on the second layer you have these variables y and x. And I'm going to come back in the next lecture to this example, and I'm going to define the height of trees, and then we are going to discuss about a little bit more about the depth or the height of these trees. But for now, just intuitively here. And finally, in the case of this example, I'm going to just trace back, how this tree is being formed. And you see that it's described as f applied to something. So I'm writing f. And f obviously has two inputs. And the first input is g of xy, and the second one is x. I'm going to write the second one because it's simpler and I'm done with. This is x on the second input. But on the first input, I'm supposed to show the tree corresponding to g applied to x of y. So that tree is obtained as, operator g applied to its two inputs, x and y. And so you see here that this is a tree that has, more layers. It has on the first layer, it has this operator f, and then on the second layer, it has g and x, and then you have x and y. And as you can imagine, this construction can be iterated, and you can have, deeper trees or trees with a higher height, as we are going to call them. But I come back to this example in the next lecture.